Hi everyone, I'm here to give you a summary lecture of F4, which is my favorite of Newton's three laws, Newton's third law. This is the first thing that comes out of F4 is Newton's third law, which I'll formalize for you in writing here. So Newton's third law says that when two objects interact, they exert equal and opposite forces on each other. I would say that this is the most counterintuitive of Newton's three laws. We saw a couple of demonstrations in the experiments that demonstrate that this is true. I'll try and re-demonstrate a couple of them. So the first one is where we have two general bathroom scales that you would weigh yourself on, but they're taped together so that their backs are pushed up against each other. Now I'm going to put this right here so that it's going against the two, these are like ring stands, I suppose, and when I push on this side, so I'm the person exerting the force, right, so I'm going to push on the spring scales. So we could consider that when I read the scale on this side, it's measuring the amount of force that I push on the scale. But we could also read the scale on this side and consider it the force that the scale is exerting back on me as I push on it. So I'm going to start pushing, and mine reads about 6 pounds. And if we look on this side, it also reads 6 pounds. No matter if I push a little bit harder, so no matter how hard I push, the scales always read the exact same amount on either side. So when I push on the scale, even though the scale is stationary, it's pushing back on me. It's the exact same if I push on a wall or something. So if I push on this ceiling wall, right, the wall's also always pushing back on me. One of the best ways that, often physics teachers give you a demonstration of this is you say, well, punch the wall. Right? You hit the wall, but why does your hand hurt at the end? Because the wall also hit you back. So anytime there's an interaction where there's a force between two objects, a push or a pull, the force exerted by an object on the other object, so on the wall, is exactly the same as the force exerted by the wall on the other object, on me. The other demonstration that we saw in the experiments for this was using pull or spring scales. So we can do a similar demonstration where I have this sling used for climbing, and if I hook a spring scale to that sling and then hook another spring scale, I actually need another piece of rope here. Give me a second. All right, new plan. So I have two spring scales hooked together because, again, we're going to consider that the spring scale that I'm pulling on measures the force that I'm pulling on this sling with. So I'm pulling on the sling, force exerted by me on the sling. And then this second spring scale that's oriented the opposite direction is measuring the pull that the sling exerts on me. So this one is the force I exert on the sling. This one is the force the sling exerts on me. So when I pull on this and I read this scale, it says 6 newtons of force. And when I read the other scale, it also says exactly 6 newtons of force. So whether it's a push or a pull, the forces are always equal and opposite that are acting on the two objects. All right, I'm going to give you a couple of examples where this typically occurs. So the intro or the initial ideas for this chapter, F4, was about when two cars collide, or two trucks, and one of them has a much lower mass than the other truck. We don't have trucks here, but we're going to use a soccer ball and a bowling ball to demonstrate this. So we have soccer ball, pretty light, less massive. Bowling ball, I could really get a workout with this one. When these two things are involved in a collision, so I'll see if I can demonstrate this. right? There's a very different reaction there. So let me do it one more time. Okay, so what you probably saw was that the bowling ball was moving towards the soccer ball, and the soccer ball was moving towards the bowling ball. The bowling ball, when it collided, slowed down slightly, but then kept moving in the same direction, whereas the soccer ball quickly reversed its direction, slowed down quickly, and then also went the other direction. Now, this is getting at the connection between Newton's third law and Newton's second law, really, which is that although they exert the same force on each other, their resulting motion is different because they have different masses. So remember that Newton's second law is really best stated in the form of an equation. So the Newton's second law is that the acceleration that results due to unbalanced forces is calculated or is directly proportional to the net force acting on that object and inversely proportional to the mass. Or if they have the same force acting on them but different masses, they're going to have different accelerations. So let's draw this out just for a second. We had our soccer ball, call that SB, and our bowling ball, call that BB. Now, if I'm going to draw the force diagrams that show the forces acting on these two objects, on the soccer ball, it was moving to the right. So it had a velocity vector pointing right. The bowling ball was moving to the left, velocity vector pointing to the left. The bowling ball, well, let me start with the soccer ball. The soccer ball collided with the bowling ball. So the force on the soccer ball by the bowling ball points to the left. So this would be F on SB on soccer ball by bowling ball by BB. The soccer ball also exerted a force on the bowling ball. So the force on the bowling ball by the soccer ball points to the right. These two forces are equal. So I'm going to demonstrate that they're equal by adding this little dash mark, just like you would in your geometry class to show that two sides are congruent. They're the exact same length. So the force on the soccer ball by the bowling ball is exactly the same as the force on the bowling ball by the soccer ball. Equal and opposite forces here. However, they have very different resulting motion because the acceleration is not only related to the force, but also related to the mass. So if I look at the acceleration for the bowling ball compared to the acceleration for soccer ball, I'm showing this with kind of capital M and a lowercase m. The bowling ball has a much larger mass, so when we divide that force by the larger value, our acceleration is much lower for the bowling ball. So we have a small acceleration on the bowling ball due to the large mass, whereas because the mass here is small, we're dividing by a small number, so the acceleration is much larger for the soccer ball, which is why we saw it quickly slow down and change direction. Now, one of the things to point out here is that these forces, what we call force pairs due to the two interacting objects, those forces always show up on different force diagrams. The force diagram always shows the forces acting on that specific object. It does not show the forces that are acting by that object. So the force on the soccer ball appears here by the bowling ball, and the force on the bowling ball by the soccer ball appears on the other force diagram. So these would be considered force pairs because they're due to the interaction of the two objects, and they appear on different diagrams. Now this is very different than the concept of balanced forces. Balanced forces always appear on opposite objects. So let me add that note over here. So some examples of balanced forces, so I'm going to do that down here, examples So examples of balanced forces would be like where you just have something that's stationary or something that's moving at a constant speed. So an example of a balanced force would be when you have a car that's driving at constant speed, and so it has a velocity, and it's continuing that speed because it has some force of thrust from the engine, but it also has an equal and opposite. So again, I'm using congruency there, but it's on the same object, force of friction that opposes its motion. So there would be example of balanced force, meaning that the acceleration here is 0. In contrast here, right, the force pairs appear on the two different objects. And in this situation, of course, the acceleration is not 0 because there's a non-zero net force acting on each of these objects. One other example of a balanced force would be when something's just stationary. So let me introduce you to my new pets, I guess, or plants pets, Khaki and Barb. These are two little cactuses that I found just stranded somewhere when I was out hiking a while ago, about 2 months ago, and they finally have rooted and now they're potted. So when Khaki and Barb are just sitting on the table here, if I look at that object, so in this case the potted plant, I can tell that the forces are balanced because I don't see any change in motion. I don't see any change in velocity. It's just stationary. It's maintaining that speed of 0 meters per second. So this would be another example of balanced forces. So let me draw the force diagram for this one, for Khaki and Barb. So in this case, we're dealing actually with vertical forces. This is not something that we've talked about yet. We've always been working with forces that are acting left to right. I'm bringing them up here because in our next unit, we'll start thinking about vertical forces, and we won't get to all of that unit, so I want to point out one of those forces. So I know that the forces are balanced, like I was saying, because I don't see any acceleration. And then I have to think about, well, what forces are acting on this? You might think that there's no forces, but there is a force, and it's the force that holds us all to the planet Earth, the gravitational force. So that gravitational force is an interaction between the potted plant and the Earth, actually. The Earth is pulling the plant downwards. So I'm going to call that force Fg, G standing for gravity, pointing straight down. However, if I look at the plant, it doesn't actually accelerate down towards the Earth, so there must be some other force that is keeping it from accelerating to the Earth. And the only thing that I can think of is that, well, this table is kind of in the way of it going down to the Earth. So with this pen, if the pen's on the table, it is stationary, but if it's off the table right there, it accelerates to the Earth. So it seems like maybe there's a force from the table that is balancing this gravitational force pushing up. And indeed there is. We call that force the normal force, or really a normal force is any perpendicular acting push. In this case, the table is pushing this potted plant upwards, perpendicular to its surface. So we label that one as a vertical upward force. And generally, it's noted as Fn, N standing for normal. So this is a second example of a case where we have balanced forces. These two forces are equal to each other, but they're not considered a force pair. The force pair has to do with the two interacting objects. All right, that's the summary that I have for you on F4. Feel free to reach out to your teachers if you have any other questions. And yeah, that's it.